When you're developing a new electronic product, it's so easy to get pulled toward the latest and most advanced technologies. But the truth is, many of these choices will make your product nearly impossible to develop, at least without a huge team, a massive budget, and years of extra time. So in this video, I'm going to show you 10 technologies that you should avoid whenever possible, because they can trap you in endless development and prevent your product from ever reaching the market. Hi, I'm John Teal. I'm a former microchip design engineer who brought my own product to market, and now I help others develop and launch their electronic products inside my Hardware Academy. All right, let's get started. Technology number 10 is high-end application processors such as those from Qualcomm and Broadcom. Now, these chips look incredible on their spec sheets, and they're what power most flagship smartphones and tablets, offering insane performance, beautiful graphics, and every type of connectivity that you can imagine. But here's the reality. They're basically off limits to startups and small teams. The data sheets are locked behind non-disclosure agreements, and you usually won't even get proper reference designs. And unless you're a huge customer, you're not getting any meaningful support. Minimum order quantities can be tens of thousands of units, and integrating the software stack is a massive job, even for experienced teams. I've seen entrepreneurs waste months just trying to get basic documentation or battling buggy drivers that were never meant for the general public. A better move is to stick with accessible platforms that actually support small teams. Microcontrollers like the STM32 or ESP32 give you plenty of power and are easy to get up and running. If you need more performance, something like a Raspberry Pi compute module gives you more horsepower, but still with real documentation, community support, and reference designs that you can actually use. And just to add, the same goes for dedicated AI and machine learning chips. These sound, of course, exciting, but they often come with really high complexity and limited software support. If you're developing a new product right now and want to avoid design mistakes that make any technology a nightmare to implement, then grab my free design review checklist bundle. You'll get separate design review checklists for your schematic, your PCB layout, and the enclosure design, the three areas where most product failures start. The link's in the description, or just scan this QR code. Tech number 9 is custom RF designs, especially sub-gigahertz. So trying to do your own custom RF design, especially in the sub-gigahertz range, is going to be a huge gamble. At higher frequencies like 2.4 gigahertz, you can at least find pre-certified modules for Wi-Fi, Bluetooth, and Zigbee. But once you drop into 433 megahertz or 900 megahertz territory, well, then you're usually on your own. That means designing antennas from scratch, tuning matching networks, and trying to pass FCC or CE testing without much vendor support. And RF is tricky. Your layout, your enclosure, even the battery wire running too close to the antenna, all of it can break your wireless performance. Unless you have serious RF expertise and test equipment, you're better off using pre-certified wireless modules or sticking to wireless technologies that come with proven reference designs and antenna solutions that you can actually use. Technology number 8 that you want to avoid is needing to design a custom battery pack. One of the most common reasons people choose a custom battery is because they're trying to squeeze in every last bit of battery capacity. If you're building something small like a wearable or a handheld device, it's really tempting to design a battery that perfectly fits the internal shape to maximize energy density. But going custom introduces a whole new layer of risk. The moment you design a custom battery pack, you're responsible for meeting strict safety and transportation standards. The testing process is expensive, time-consuming, and failure-prone, especially for small teams without dedicated compliance engineers. On top of that, you'll face delays if your certification lab finds anything questionable, and you'll have to source specialized suppliers who can build packs at low volumes while still supporting traceability and quality control. A far safer and faster approach is to stick with off-the-shelf batteries, such as pre-certified lithium polymer packs. You won't be able to use 100% of the available internal volume for your product, but you'll avoid a year-long certification slog and a major liability risk if something goes wrong. Tech number 7 to avoid is advanced USB features. Advanced USB features like USB 3.0 super speed or USB power delivery sound fantastic on paper. You get higher data rates, more flexible power delivery, and modern compatibility. But both of these features come with some serious implementation challenges. USB 3.0 runs at 5 gigahertz per second or more. To get that working reliably, you need carefully matched differential pairs, very tight impedance control, and a multi-layer PCB stackup that supports high-speed routing. And debugging issues is no small feat either. You'll need expensive tools like high-bandwidth oscilloscopes and signal integrity test setups, tools that most small teams don't have access to or that can't afford. USB power delivery is another beast. It lets your device negotiate power profiles up to 20 volts and 5 amps, which sounds great if your product needs that kind of power. But it also means adding a dedicated power delivery controller chip, firmware to manage voltage negotiation, and precise power switching. Unless your product truly needs high-speed data or more than 5 volts from USB, you're better off keeping things simple. USB 2.0 for data, it still gives you 400 megabits per second, and for power, stick with just a 5-volt USB charging or a DC barrel jack. USB power delivery is great when you need it, but you definitely need to know what you're signing up for. Tech number 6 is wireless charging. Wireless charging feels futuristic, and for marketing, it really sounds great. Just drop your device on a pad and it charges. But under the hood, it's a different story. Coil alignment has to be perfect. Thermal issues come up fast, and efficiency is much lower than wired charging. And if the power transfer is inconsistent, customers start complaining. On top of that, Qi certification isn't cheap, and that is the standard for most wireless charging. And inductive charging introduces a whole new mess of EMI issues that are hard to troubleshoot. Unless wireless charging is a must-have feature for your product, then you're going to get better results just using a USB-C port, pogo pins, or even a custom cradle. These options still feel sleek, but they're far easier to implement and much more reliable. Tech number 5, proprietary or high-speed connectors. So it's easy to be tempted by sleek modern connectors like MIPI, Thunderbolt, or even Apple's Lightning connector. They look clean and offer blazing fast data rates on paper, but integrating these can be brutal. You'll often need expensive test fixtures, detailed timing analysis, and access to documents you can't get unless you're a high-volume partner. With Apple's Lightning connector, you're also dealing with licensing fees and per-unit royalties through their M5 program. Unless you're shipping millions of units, you won't have the support or the leverage to use these interfaces safely. Stick with more accessible standards like SPI, I2C, LVDS, or HDMI. They're not maybe as flashy, but they're far more forgiving, and they won't block you from getting to production. Tech number 4 to avoid are overly fancy displays. An active matrix OLED screen like the kind used in smartphones and tablets can make your product look really cool and modern, but despite how amazing they look, these displays are usually a bad choice for small teams. They often require a MIPI DSI interface, which isn't supported by most microcontrollers. That means you'll be locked into using a more expensive application processor, even if the rest of your product doesn't need that kind of power. The cost of these displays themselves are also high. They're typically priced for large-scale phone manufacturers, not low-volume hardware startups. Even worse, these panels have short lifespans in the supply chain. A model might be discontinued without warning or replaced by a new revision that isn't compatible with your existing design. Even when you get documentation, integrating them takes time. Managing the initialization sequences, voltages, backlight control, and timing. For most projects, you're much better off with a standard TFT LCD from a supplier like New Haven or buydisplay.com. Stick to common resolutions and simpler interfaces like SPI or parallel RGB. You'll avoid being locked into an expensive processor, and you'll have a much smoother path to production. Tech number 3, high-end analog audio. Audio seems simple, it's just sound, right? But high-end analog audio is one of the most unforgiving parts of electronics design. Your layout matters, grounding matters, shielding matters, power supply noise matters. Even tiny mistakes create hiss, hum, or distortion that customers will definitely hear. And validating these designs requires test equipment that most small companies don't have access to. If you don't have serious analog expertise on your team, don't try to go toe-to-toe with audiophile grade products. Instead, use digital audio interfaces like USB, I2S, or Bluetooth modules where the hard stuff is handled for you already. And if you need analog, start with something small and copy the reference design exactly. Technology number 2, 5G or cutting-edge cellular modules. 5G sounds like the future, and for some applications, it's really beneficial. But for most startups, you don't need it, and trying to integrate it usually ends up being a huge drain on your resources. These modules are expensive. They often require specialized SIM provisioning, thermal design considerations, and compliance testing with cellular carriers. And just because a module is pre-certified doesn't mean your end product will sell through certifications. If your antenna tuning, ground plane, or enclosure affects performance, you could be forced to go through carrier testing all over again. In most cases, you'll get better results using pre-certified LTE, Cat-M1, NB-IoT, or even 4G modules. They're cheaper, easier to source, and way more forgiving, especially for low to medium bandwidth use cases. Unless your product truly requires high throughput and real-time video or data streaming, 5G is usually more pain than it's worth. Do you want to avoid costly design mistakes? Then be sure you grab my free design review checklist bundle covering the schematic, PCB layout, and enclosure, the 3 areas where most products go wrong. Links below or scan this QR code. Technology number 1 to avoid in your product, if at all possible, is custom IC design. This one comes up more often than you'd expect, especially with wearables or ultra-compact products. Founders get the idea that the only way to fit everything into a tiny enclosure is with a custom IC. And in theory, that's true. Custom silicon lets you combine everything, radios, processors, memory, everything into one sleek small package. But in practice, custom chip design is a mountain you do not want to climb. We're talking about massive upfront cost, long lead times, highly specialized engineering, and extremely expensive prototyping cost. Unless you're building the next Apple Watch and you've raised millions of dollars, this is not the path to take. Startups should stick with off-the-shelf chips and proven modules. If you found this video helpful, then these are the 2 videos that you need to watch next.